Assalamualaikum warahmatullahi wabarakatuh and good night everyone. Okay, Alhamdulillah we continue stiffness method, for beam structure. Okay, we are going to continue to analyze a continuous beam. Okay, so in the first session this morning we actually discuss about this beam. Okay, this beam ABC. So this beam has three nodes or three joint A, B, and C. So in total, there are 6 degree of freedom. There are 6 degree of freedom, and for beam, we have to label degree of freedom in X and not X in Z and in Y and X and Z component. In Y and Z component, not X, because we don't have to consider X component. We just need to consider Y component and Z component, Y and Z. Okay, so there are two DOF per node, YZ, YZ, YZ. Okay, and remember, whenever we label the degree of freedom, we have to make sure that we label it according to unconstrained and constrained system. Okay, we have to label it according to unconstrained and constrained system. So basically constraint refers to number of unknown reaction. Number of unknown reaction, there are two at A because A is fixed, where we don't have to consider AX as degree of freedom. So we just consider Y, and Y means AY, and Z is MA reaction AY and reaction MA at support A. And at point B, at joint B, we as we know, there are BY and CY at B and C, BY and CY. So that is why we have 4 degree of freedom in constraint system. So in total, it must be 6. So there are two remaining. Okay, there are two remaining which we put at B and C, and in unconstrained it represent rotation at B and rotation at C. So D1 and D2, D1 and D2 representing rotation at B, rotation at C. Okay, so for stiffness method, basically the procedure are the same. Same with stress analysis. We will start with establish element global stiffness matrices. Element global stiffness matrices. So element we write in small letter K1 and K2. Okay, K1 and K2. So we have to divide into elements. So that is why we call this as element stiffness matrices, K1 and K2. And the label that we use for the degree of freedom, okay, must near to far n. It is near to far n. And for beam analysis, we always assume that it is going towards right direction. So we get K1, we label as 3451, and K2 we label as 5162. Okay, near to far, so left to right. Okay, so all the value in the matrix we get from formula. The formula is given in appendix. The formula is given in appendix. It is 4 by 4 matrix. 4 by 4 matrix. Okay, so in order to calculate the stiffness factor, this is the stiffness matrix K1 and K2. It actually influenced by E is material properties, modulus of elasticity. I is section properties. We calculate from the cross section area. We calculate moment of inertia, and another thing that can influence the stiffness value is the length of the element. The length of the element. So we get K1 and K2. I hope you have determined the value. okay, this value, so that we can complete this question at the end of this session. Okay, and after that, as usual, we have to combine to have the structure stiffness matrix. The structure stiffness matrix, it is capital K. It must be written in order. It must be written in order. Don't forget to put EI. Don't forget to put EI, because we just need to produce in terms of EI first, the K value. Okay, and of course, when it has unconstant EI, we have to consider in K1 and K2. Okay, so we have to find all the value, start from position 1 1 until 6 6 in K1 and K2, as usual, just like what we have done previously in trust analysis. So the label that we put, the label that we put in the label that we put, okay, in K1 and K2, is actually representing the position in the structure stiffness matrix. So we have to plus the same position 1 1, 1 2, 1 3, and so on until 6 6 position. So we have to put all 6 6 value to have the structure stiffness matrix. Okay. Uh, that is the first part. That is the first part. And we have to understand that whenever we analyze beam, okay, the stiffness equation is not only Q is equal to KD, because normally the member, okay, for example, member AB is subjected to UDL. Okay, UDL means loading that is subjected on the member. And always remember that in stiffness method, we can only analyze forces and displacement at nodes. Okay, we cannot determine mid span deflection, cannot. Okay, so we will calculate all the value at nodes. We have to calculate the value at nodes. So whenever the element is subjected by UDL or point load at the center or at anywhere on the member, but not at nodes. Okay, so we have to consider it as equivalent nodal forces. We label as Q naught. We label as Q naught. So this session we will focus on how to determine the value for Q naught. Okay, so that's what we are going to do in this session. Okay, so this is the equation look like the stiffness equation or force displacement equation. Okay, I have explained to you how we identify the value, start from position 1 until position 6 for Q, and the displacement start from position 1 until position 6. Why displacement at position 3 until 6 become 0, and why the value for position 1 and 2 in Q become 0. And I believe you have calculated the K value, okay, the matrix, okay, in the matrix. And now we are going to focus on Q naught. Q naught. This is Q naught. This is Q naught. Okay, there are six value based on six position. Based on six position. So we have to analyze this from element equivalent nodal forces. In total, okay, so we move to the concept of equivalent nodal forces. It is equivalent nodal forces. Okay, just add this word. Nodal forces is Q. Equivalent nodal forces Q naught. Equivalent nodal forces Q naught. Okay, this Q naught. Okay, this Q naught means we have to distribute. We have to distribute the loading equivalently. We have to distribute the loading equivalently. We have to distribute it to nodes. So we do not set equally. we do not set equally uh, because this one, okay, let me show you appendix that is normally given in past year's exam papers. Okay, in past year's exam papers, appendix stiffness method. Okay, so this is beam. This is the formula. The formula. So we can see that beam has same local and global coordinate system. Same local and global coordinate system. That is why we can find only one formula for K prime and K. Okay, this is for the K formula. And when we move to, okay, I want to show to you appendix page 3. This is only page 1. Okay. Okay, this one is called as fixed end action. This is called as fixed end action. Fixed end action. Okay. For the moment, we call this as fixed end moment. Fixed end moment. Okay, we call this as fixed end action because in this fixed end action we have to consider not only moment, not only fixed end moment, but we need to consider the vertical reaction as well. So that's why the name is fixed end action. Okay, fixed end action. So you have used this actually in diploma, I believe. Okay, in moment distribution method, beam analysis. So that is called as fixed end moment. Okay, it is actually part of fixed end action. Fixed end action. Okay, so fixed end action is behavior. Okay, behavior of this beam. Okay, when subjected to loading. When subjected to loading. As we can see, all this referring to the element which is subjected by loading. Okay, for number one. Okay, let's look at number one. This member is subjected to UDL along the member. Along the member. Okay, it is on top of the member. Along the member. Okay, and number two, the triangular load. The triangular load is subjected on the member as well from the first point, point A to point B, a triangular load. Okay, that is why just now I said we do not set equally. Equally can apply whenever can use whenever it is UDL, because UDL is look like one rectangular. So rectangular is symmetry, right? So for the fixed end action, vertical reaction, and fixed end moment, we can find that the formula will be the same. Will be the same because it is equal. It is equal because of the geometry is equal. So that is why we find that the fixed end moment for this, okay, the fixed end moment for this, and the vertical force, okay, all this is equal. Okay, for the vertical reaction, it is W times L, because the length is L. It is W times L, and we divide by 2, so we get here as WL over 2 and WL over 2. And for moment, the formula is WL squared over 12, WL squared over 12. Okay, so we distribute it equivalently. Okay, we distribute it equivalently, but in this case, because of because UDL is symmetry, so that's why we get like this. Okay, we get like this. So loading, a member cannot carry load, we have to distribute it to the nodes, we have to distribute it to the support. So whenever we analyze the equivalent element of the forces, we have to assume that both ends are fixed. Okay, both ends are fixed because fixed has moment. Okay, however, when we have this triangular load, okay, the vertical reaction at A and B, as well as moment at A and B, is not equally. So that is why we call this as equivalently. It depends on the geometry of the loading, the geometry. Okay, so for the triangular load, we cannot get equal value of forces, vertical reaction, and moment at support A and B. Okay, we cannot get the same value. It is equivalently. Okay, we have to distribute it to the nodes. Okay, so that's why we get four different formula for moment and for reaction, for vertical reaction at support. Okay, so type number 3, this is point load. This is number 3, type number 3. This is point load. Point load that is subjected at the center. Again, when it is subjected at the center, it is also equal. Okay, so that is why for the vertical reaction, because the system must be in equilibrium, right? Okay, so this is P over 2. This is P over 2. Okay, P over 2 and P over 2. Moment at A, moment at B, opposite direction. This is PL over 8 and PL over 8. PL over 8, PL over 8. Okay, this is whenever P is subjected at the center. Okay, now we look at category number 4. This is category number 4. P, the point load can be subjected not at the center. P is subjected not at the center. So from A, from support A, we label the distance from support A to P. So we label as A. We label as A. And from support B, okay, to P, we label as B. Okay, A and B is not A, the shortest is A, the longest is B. No. Okay, as long as it is between A and P, it is A. Okay, A and B will be different depending on the node number. Okay, so means that at left, from left it is A, from right it is B. And since P is subjected not at the center, P is subjected not at the center, so that is why we can find that here the formula to calculate moment at support A and B, and vertical reaction at A and B, all all are not equal. So there are four different formula. Okay, so for stiffness method, for this topic, uh, it is just enough to understand these four. Okay, these four type of loading. These four types of loading. Okay, type number 1, 2, 3, and 4. Okay, there are four, right? So this is number 1. 1, 2, 3, and 4. Okay, so actually we will use again this formula in topic number 3, moment distribution method. Uh, Okay, about the sign. Okay, about the sign. Okay, so whenever we have uh, okay, to analyze equivalent and element nodal forces, fixed end reaction. So we have number one, we have to assume that both end are fixed. That is condition number one. Both end assume as fixed. Both end assume as fixed. Okay, the distance is L in meter. The distance is length in meter. Okay, this beam is subjected to loading. Is subjected to loading. Okay, so this is W. W. Okay, so always remember that the system must be in equilibrium. So that is why we will get the vertical reaction as WL over 2, because we can see it directly. That's the behavior. Whenever this is P, so we will have P over 2, P over 2. Or when it is WL, WL, so what we get is WL over 2, WL over 2, because WL we get kilonewton. Okay, but what about the behavior, the moment direction for A and B? For A and B. Okay, it is not a sign convention that you can just assume. It's not that. Okay, it's not like when we calculate reaction, we can assume that moment is acting clockwise or counterclockwise. Cannot. Okay, because fixed end moment is behavior. Fixed end moment is behavior. So the moment that we put at A and B is not assumption, but it is behavior. Behavior. So just imagine this beam whenever subjected to loading. Okay, this beam whenever subjected to loading, whatever lah, whatever member when subjected to loading, it will bend. This is the behavior. Okay, the beam original is straight position. Original means when there is no loading, it is horizontal. That is original. Original is horizontal. This is original position. Horizontal position. Beam is horizontal member. This is original position. Okay, due to loading, either it is UDL, or it is triangular load, or it is point load. Okay, we will find that the beam will deflect. The beam will deflect. And the moment at the reaction moment at A and B, at support A and B. Okay, the moment that exists will actually push this point and this point. Okay, moment is going to be like this, because the moment will push the new position to its original position. Okay, push back to original. Okay, the moment is behavior. Fixed end moment is behavior. Okay, due to loading, the beam deflect, bend. Okay, so when we apply, not we apply the, because of the support reaction, because of the fixed support, we assume that both end are fixed. Fixed end reaction, fixed end action, we have to assume that both end are fixed. That is why we get moment. Okay, so due to that, the moment will push back the beam to its original position. So we have to push this in this direction, so that this one will move back to straight. Okay, that's why we apply the moment counter clockwise at A. And at B, we have to apply in this direction at B, we have to apply in clockwise direction so that the band beam, okay, it will push back to its original position. So that is why fixed end moment, the moment is always due to loading, it always going to be like this. Okay. So if loading is come from this, okay, so the moment it will bend like this, bend like this. So moment we apply, okay, opposite with, okay, the upper one, opposite, because the loading is opposite. The due to bending, due to the beam after deflection. Okay, so we have to apply fixed end moment to counter back, to counter back. Okay, that is for beam. That is for beam. So let's say it is column. Let's say it is column. Loading is come from this side. Okay, so look at what happened to the column due to loading. Bend like this. Okay, so when bend like this, when we have to apply moment at that is exists at support A and B. Okay, we'll push back this to its original position, to its original position. Okay, so another one, if loading is come from this side, okay, maybe UDL from this. Okay, so bend like this. So moment will push this and push this, because this one must be straight back. Okay, so the moment is acting like this, means that fixed and moment or fixed and action, okay, all behavior. The sign convention that we put here based on the behavior, not assumption. Okay, not assumption. That is about the fixed and action. Okay, so just a simple formula for 1 and 3. Anyway, the formula will be given to you. Okay, so we go back to this. Okay, equivalent nodal forces come from combination of equivalent element nodal forces. Equivalent nodal forces come from combination of two element, combination of Q, Q naught for element 1 and Q naught for element 2. Okay, Q naught for element 1 and Q naught for element 2. Okay, so Q for element, we use small letter. This is small letter because it is for element. Capital letter because it is for the whole, 1, 2, 3, 4, 5, 6. Okay, so we have to analyze this one by one element. We start with element number 1. Okay, element number 1. So element number 1, member AB. Okay, in this case, there is no value. There is no value because there is no load on member AB. There is no load. Okay, so for element number 1, it is Q not for element 1. Q not for element 1, Q not for element 1. For value, for value, and since the value is all 0, okay, so we just need to put 0. So 0, 0, 0, 0. Why for value? Because it is for element. One element, two nodes. So we have to label same like K1 label. Same like K1 label because it is element number 1. Element number 1, refer back to this element number 1. It is 3451. 3451. So this is 3451. Okay, the value is 3451. Okay, now we focus on element number 2. Element number 2, for element number 2, element number 2, okay, so it is assumed that it is fixed. It is UDL, UDL 10 and 10. Okay, 10 and 10. Okay, this is 10 kilonewton per meter along 10 meter length. This is B and C. Okay, so this is the formula. This diagram based on the formula given. Assume that both ends are fixed. So imagine the behavior. Okay, there will be reaction, reaction, and a fixed end action, two vertical reaction, and two moments. Okay, for vertical reaction, it is WL over 2. WL over 2. So here is WL over 2. WL over 2. And for moment, for moment acting like this, M at B, moment at B, fixed end moment at B, counterclockwise, fixed end moment at C, clockwise. That is behavior. Behavior. And the formula is WL squared over 12 and WL squared over 12. Okay, so this is based on the formula given. Based on the formula given. Okay, what we need to do next is we draw the diagram and the DOF label. The element number 2, this is element number 2, element number 2, this is element number 2. Element number 2, A and B, B and C. Okay, the label, the DOF label that we use, okay, okay, the degree of freedom, it is 5162, right? 5162, same like K2 label. 5162. 5162. Okay. Okay. So for the Q not for element 2, Q not for element 2. Okay, there will be four values, four position based on four position. Okay, four values, and the label should be 5162 near YZ, far YZ. 5162. 5162. 5162. Okay, 515. So this is 5. 5 is WL over 2. WL over 2. And WL over 2 is equal to, what is the value? WL over 2. This is 10 times 10 divided by 2. 50. Okay, WL over 2, because this WL over 2 is 50, right? 50. And 5, position 5, position 5, okay, these two are equal, same position, same direction. 5 equivalent to, at position 5, the value at position 5 equal to WL over 2. It is 50. Same direction means it is positive. So it is 50. Okay. Okay, next value, position 1. Position 1. Position 1. Okay. Position 1. This is position 1. So the value for position 1, okay, is this value. It is Z component. Z component. Okay, Z component. Okay, previously it is Y component. Now it is Z component. We compare these two. Okay, for position 1, it is moment WL square over 12. However, the moment, the moment are opposite. Okay, the direction, the moment direction. Okay, the for fixed end moment it is counterclockwise, but the sign convention, okay, sign convention is this. This is the sign convention. Z sign convention clockwise, counterclockwise as well. So same direction. This is counterclockwise. This is also counterclockwise. Counterclockwise, counterclockwise. The value is WL squared over 12. WL squared over 12. Please calculate for me what is the answer. WL squared over 12. W is 10. L, WL squared. WL squared over 12. Please calculate what is the answer. It is 1000 divided by 12. 500 divided by 6. Okay, what is the answer? What is the answer for this? 3, 250. 250 divided by 3. 83.33, yeah? 83.33. So the value is 83.33. It is positive. It is positive because it has same direction. Same direction. Okay, next. Okay, next we want to find the value at position 6. Find the value at position 6. Okay, 6. This is 6. Okay, 6. Okay, equivalent to this. Okay, and same direction. Same direction. It is 50. 50. Okay, and last one. Last one, position 2. Position 2. Position 2. This is position 2. Okay, this is position, the value for position 2. The direction, the direction is is opposite. The direction is opposite. Okay, the direction is opposite. So when it is opposite, it is negative. So it is WL squared over 12, 83.33. Okay, the direction is negative. The direction is opposite. These two is opposite. So we have to put negative. So when it is opposite direction with when we compare these two, so we put negative like this, like this. So we have to combine. So Q naught. So Q naught equal to Q naught element 1 plus Q naught element 2. Q naught element 1 and Q naught element 2. We produce 6. Okay, the sixth value based on 6 position. Okay, based on 6 position, 1, 2, 3, 4, 5, 6. Now we find the value at each position from Q naught 1 and Q naught 2. Okay, and since Q naught 1 has no value, so we just focus on Q naught 2, this one. Okay, so for position 1, position 1, position 1, position 1 is this value. Okay, position 1 is Okay, position 1 means we have to find the value we label at as at position 1 in Q note 1 and in Q note 2. Okay, and the value is 83.33. So we put at position 1. So this is 83.33. Then we find the value at position 2. The value at position 2 is negative. This is negative 83.33. Okay, next is position 4. There is no position 3, position 4. There is no 3, 4 here. Okay, means 3, 4 is under Q note 1 and the value 0, 0. Okay, and 5, 6. 5, 6 we get here. It is 50, 50. 50, 50. So this is 50, 50. Okay, so this is called as equivalent nodal forces. Equivalent nodal forces. So uh, there are notes you can find some notes that combine Q and Q note under one formula. Q is equal to KD, and normally using that method we will determine the value of Q and Q note, not like this, not like what we have done tonight. And I will not show you that step because it is quite confusing. So I want to suggest you to follow the equation for the equation, the stiffness equation, considering Q and Q not separately like this. Okay, we settle part by part, means part by part we settle Q. We settle Q part, and then we settle Q not part. Okay, under separate step. And after that we will substitute this into the equation. Q is equal to KD plus Q naught. Q is equal to KD plus Q naught. Okay. 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 So normally you have to read the question given carefully, because in examination you have to understand the question. Sometimes you don't need to give the stiffness equation in full. In full means Q all 6 degree of freedom. You don't have to do that. You don't have to do that. You need to have stiffness equation. You need to have stiffness equation corresponding to unconstrained degree of freedom only, because we get displacement, unknown displacement, by only considering unconstrained system, and it has only 2 degree of freedom. Okay, we don't have to consider all. Means that, okay, from this equation, it will be depending on this 1 and 2. 1 and 2 means this is in full, and we have to have this picture in mind. Okay, we have to have this picture in mind. But in order to solve D1 and D2, we just need to consider these two 2 by 2. Okay, this D1 and D2 and these two. So actually we don't have to have this. We don't have to have this. Okay, so that is why you have to understand the question carefully. So please give the answer according to the question. Okay, not uh, based on uh, based on remembering everything, because that is the step. You remember all the step. You want to give in full solution. No. Okay, always give the answer based on the question asked. Okay, normally when the question is to calculate displacement, the compulsory step to calculate displacement, unknown displacements, compulsory K1 and K2. This is compulsory. K1 and K2 in full. 4 by 4 for K1 and 4 by 4 for K2. This is compulsory. Okay. Uh, After that, you have to combine. You have to combine K from K1 plus K2, but you don't need to give in full as well. Just need to give 2 by 2, depending on degree of freedom. If the unconstrained has 2 degree of freedom, so we give 2 by 2. We have to have 2 by 2. If the unknown displacement from unconstrained, there are three unknown displacements, so we have to give 3 by 3, 3 degree of freedom. Okay, so this step are all compulsory step whenever the question asking you to calculate displacement. Okay, number three, the stiffness equation. uh the stiffness equation, of course, you have to have you will use this equation KD plus Q naught. This is stiffness equation or force displacement equation, but you don't need to give in full because what you want is only 2 by 2. Okay, D1, D2 plus 2, the value for position 1 and 2 only. Okay, this is 1, 2 until 2, 2. This is 1, 2. Okay, so is called as stiffness equation corresponding to corresponding to unconstrained degree of freedom system. Okay, these are all the steps whenever the question asking you to give displacement. But if the question A establish uh, element stiffness matrices, B establish structure stiffness matrix, C establish stiffness equation, D calculate unknown displacement, then you have to give in full. But if the question directly asking you to give displacement, so you just need to focus on how to get displacement. Okay, how to get displacement. So actually, uh, you just need to give short solution because you don't have to give in full. Okay, so one and two, we get 0, 0, right? 0, 0. So this is EI. Okay, EI. So we get D1 and D2 here for the unknown rotation at B and C, and we have to plus with Q naught 1 and 2, 83.33. So here is 83.33 and negative 83.33. Okay, this is enough. Okay, to calculate unknown displacement. By solving this equation, we get unknown displacement. So we simplify this because this equation, this unknown displacement, we will get from actually two simultaneous equation. So we rewrite back this equation, EI D1 D2 D1 D2 equal to, so we have to bring this right, 0 minus 83, so we get here negative 83.33 and positive 83.33. Okay, if EI is given, you want to divide by EI also okay. If EI is not given, you just can give the value of D1 and D2 over EI like this. Okay, over EI like this. Then you get D1 in terms of EI and D2 in terms of EI. Okay. So once you get this, you can continue to calculate reaction at the support 3, 4, 5, 6 position, right? Okay, same procedure like what we have discussed in thrust analysis. Okay, whenever displacement okay has been determined, okay, use back the displacement, we substitute back into the stiffness equation. Means that in the okay, that is why this equation we must have in full picture in mind. Okay, because whenever we want to calculate Q3, 4, 5, 6, we want this part. Okay, so we have to know the position from K1 and K2 because here is 3, 1, 3, 2, right? 4, 1, 4, 2, 5, 1, 5, 2, 6, 1, 6, 2. So all this position we can find from K1 and K2. Because in order to calculate Q3 it is, remember, we have discussed quite detail under thrust analysis previously during online session as well. Okay, to calculate reaction Q3. Okay, Q3, it is actually value 31, we times what with D1, right? And the value at position 32 we times with D2. And after that we have to plus Q naught, Q naught at position 1, position 3. Q naught at position 3. Okay, Q naught at position 3. So same goes to Q3, Q4. But be careful with the sign. Okay, because in Z we must put kilonewton meter. Okay, so 4 means the value at position 41, 41, 41. We calculate with D1. And the value at position 42, we calculate with D2. And we have to plus with Q naught at position 4. Okay, that is for the reaction. And and Q5. Just continue. Value at position 151 time with D1 plus value at position 52 we times with D2 we have to plus with Q naught at position 5. This is for reaction. Okay, and Q6 61 D1 plus 62 D2 plus Q naught at position 6. So all this is actually the matrix multiplication. This is the process. This is the process to get reaction. So all this process we write back from actually the the stiffness equation in full. The stiffness equation in full, but this okay, this picture you just need to imagine in mind. Okay, so when we want to calculate this, we need this time with this plus with this. So so this is the matrix multiplication actually, and the process is like this is for the reaction. So once we get reaction, we can continue. Okay, we can continue to draw shear force diagram and bending moment diagram. Actually, in the in you future, in the you future, you can find the okay the notes. Okay, one full example I have put in the you future. Okay, please find notes there. Okay, there are some example given from beginning, okay, until the diagram, because this beam after all loading, okay, this is UDL, right? UDL. So we get this value, and this value, and roller. So we get moment here. So we should be able to draw diagram. Okay, there are some example given in the U feature. I've uploaded that. So you can find that one also, and also in the Padlet, yeah, in the Padlet also, for stiffness method, I have actually put the link for website. Okay, for my own website. Okay, discuss some example until the diagram, the shear force diagram and bending moment diagram. So basically, it is like this. Okay, go straight, and then like this for the shear force diagram, and for moment diagram, because moment is come from the area of shear force diagram. Okay, later I will set another session just to discuss about shear force diagram and bending moment diagram. So for the bending moment diagram, okay, this point and this point join together, okay, and then intersection maximum moment. This is zero moment because of roller, so it is basically like this for the bending moment diagram. So the value we should get, the value in the diagram we should get after we get all the reaction. Okay, the reaction Q3, Q4, Q5, Q6. Okay, so continue to solve this. Okay, continue to solve this example, except group 7 7B1. This is for 5B D1. You have to complete this. Okay, until the reaction, yeah, until here you have to complete. You have to complete all this until reaction, and try to draw the diagram. Okay, just try to draw a diagram. You can find also my previous video explaining about diagram. Okay, finish until this, and additional is the diagram. Please try to do. Okay, for 7B1, you complete this. Okay, complete this. Okay, this is another beam example. So this is website actually. You can find this question in the Padlet. Okay, I want you to complete this, and you have to submit this. Okay, can can or not? Okay, every group have to submit this question. Every group. Okay, uh, just for group D1, because this is first time, right? So you just try to understand this example first. Try to understand this example. This is very, very important. This is very important because in final exam there are two question. There are two question from stiffness method. Stiffness method. Trust. beam and frame. Truss beam and frame and beam. Uh, so just look at the trend in final exam, final exam paper, and you will find that there are so many question. There are so many beam question. Okay, in final exam. So this is very very important. Actually, the solution is quite straightforward. This because this is the first time you learn about this. So look like there are so many things to write and to do, but actually you just need to do all this. Okay, so I will put example like what we have I have discussed previously with previous student. You can also watch video. Okay, watch video regarding stiffness method. So stiffness method, actually there are two questions in final exam, and it is quite straightforward, and every student can score this topic easily compared to flexibility method. Okay, so please don't take for granted. Okay, try to understand, not remember. Okay, try to like this topic. So this topic is actually very easy compared to the other, because the others, because this is just mathematical, simple mathematical solution. Okay, concept must there. Okay, you have to understand the behavior, the you have to be able to illustrate the numbering that we use. You must be able to imagine in diagram. Okay, cannot remember, but once you understand this, you will find that the stiffness method is the easiest topic, and you can actually score full mark for your final exam. Okay, so continue to do exercises daily. Okay, for this topic, and I will give the link for submission by by tomorrow. Okay, group L7B1, I give you the link by tomorrow. Okay, for group 5D. Okay, try to do okay this first, and you have to submit the other one. You have to submit the other one. Okay, by end of this week. End of this week. This one. Okay. So this is quite simple compared to the example discussed in terms of the degree of freedom position. Okay, try to do this. Okay, thank you very much. That's all for this session. Thank you. I want to announce that on 14, 14 December, 14 December, Thursday night. Thursday night, please block your activity, because night 14 December night, Thursday at 8 p.m. We have one slot for sharing session from industry panel, not panel in. So I actually invite one practitioner from consultant, okay, to give sharing session about structure analysis, how we apply structure analysis during work, okay, as design engineer in consultant. 14 December, Thursday night. Okay, please block your calendar. Okay, so that's all for this session. We will meet again in next week. Okay, next week we will continue another example. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.